So the second speaker of this morning's session is Jeremy Kahn. Jeremy Kahn, who will speak about elephants and renormalization.
Thank you. So no elephants were harmed to make this talk. This elephant was taken out of the Mandelbrot set they're sort of marching out of the cusp, and it has a truck sort of touching the next elephant. And I'm going to be talking about sort of life inside these small Mandelbrot sets. And in fact, you have to imagine elephants then marching out of the cusp of this, and then you take a small Mandelbrot set in there, and so forth. So we're getting deeply inside of the eye of the elephant. It's great pleasure and privilege to be speaking here at the 25th anniversary of the IMS. It's been my home away from home when I was poor and slightly crazy, and now I'm comfortable and well off and still crazy, and it's a privilege to come back. So, right, so this talk probably has 3 parts. Let's see, so first part will be mainly kind of, certainly expository, just kind of introductory, and it'll be mainly about the combinatorial type. So let me put it that way. Well, let's just say the type of a renormalization. So I'll just define all these terms, define renormalization, define type. And then part 2 will be kind of, I don't know what the word for it would be, but sort of summary of results and ideas, sort of outline of the approach. And then third, which may be kind of primarily for those who have some experience of working on these kinds of problems, it's probably best stated as, just some amount of details. All right, so let's start just with part 1. So, so we're, of course, this is taken from the Mandelbrot set, so we have fc of z equals z squared plus c. And at first we're interested in critically periodic polynomials. So suppose fcn of 0 equals 0. Okay, so then the critical point is periodic of period n. And so the first notion I really want to define is the Hubbard tree, which might be familiar to many, if not most of you. So the idea, let me just draw a kind of example. Well, let's draw, so here's a kind of caricature of the Mandelbrot set. And what I'm emphasizing here and drawing perhaps out of proportion are some of the hyperbolic components of the Mandelbrot set. I think kind of vastly out of proportion, but that's okay. And of course, there's ones down here, but we don't talk about the ones down there. And then in each one of these, we have a center where the map is critically periodic. And we could describe, I can write down here in these little balls the periods of the critical point. Some of these should be even larger for me to fit in these numbers. Okay, something like that. But just knowing the period of the critical point, it doesn't give you that much information about really what's going on with this dynamical system. So what's much better is to have this Hubbard tree So this one here would look like this. Let's put it down here. So here's 0, 1, 2, 3. So the idea is this is a kind of caricature of the Julia set. This is the periodic cycle goes through, it has length 4. 0 stands for the critical point, and each of these are iterates of the critical point. And then there's pretty much a unique way of connecting these attracting basins, the immediate attracting basins, within the Julia set to form this Hubbard tree. Okay, so the whole Julia set would have a lot more decorations and have a lot more little disks in between. But if you just look at the orbit of the critical point and then connect it in a kind of pretty much the only way within the Julia set, then you're going to get a picture like this. Okay, so that's the Hubbard tree. And maybe even right now I'll relate it to the elephants. So here, if I take, okay, so 2, 3, 4, and so forth. So there's a kind of, these elephants are going to correspond to a sequence of critically periodic ones kind of connected within the Mandelbrot set on these internal rays of 1/2, 1/3, 1/4, and so forth, going all the way down into the cusp.
Does the tree specify that limb 4 over there, or you need a map on the tree?
So what's important here is this topological disk tree and the labeling of the disks. The labeling is essential. Otherwise, we could have a whole lot of these trees coming from different places in the Mandelbrot set that would be labeled differently. So the labeling is essential. This sort of numbers within the trees.
Sort of respecting this labeling.
Yes, right. Thank you, Misha. Yeah. So, so this is, as I said, this is essentially embedded inside of the filled Julia set of the map. So each one of these edges kind of maps homeomorphically into the tree and kind of stretches over some number of edges. So, and the dynamics is simply determined by the numbers in the disk, because each disk maps to the next numbered disk. Okay. So then,
The entropy of the map restricted to the Julia set? 12.
it's the entropy kind of the spine or something of the Julia set. It's certainly the entropy on the whole Julia set is always 2. And the entropy on the Hubbard tree is always less than 2. So we should be, sorry? Log 2. Thank you. Log 2, yes. The eigenvalue of the associated matrix will be 2. Will be less than 2 in this case. Okay, so now let's talk briefly about renormalization. So there's this notion of a quadratic-like map or a polynomial-like map, and again, this goes back to Dewey and Hubbard. So the basic picture, which again will be familiar to a great many of you, is that we have a set U and a set V, and G from U to V. Well, if it's quadratic-like, it will have degree 2, and it will certainly be holomorphic, like everything I'm going to talk about, basically. And then the idea is that U should be compactly contained inside of V, and then we can form this filled Julia set for G, which is a set of points that stay inside of U under all iterates of G. Okay? And then, well, do this, we have the notion of renormalization. So maybe down here, like for this picture, I can have this kind of V0 that maps to V1 to V2 to V3 to V4. So all these maps are f sub c. So this becomes f sub c to the fourth. If I choose, there's a small copy of the Mandelbrot set that includes all this stuff in here. So if I choose something in this small copy, so this is some C right here, well, kind of C0, and then there's the Mandelbrot set for C in the Mandelbrot set corresponding to that kind of center, then I can get a sequence of disks such that the orbit produces this quadratic-like map, that the return map at time 4 produces this quadratic-like map. And therefore, I get a collection of small Julia sets. I get the small Julia set for this quadratic-like renormalization, and then all of its images. And after 4 steps, it comes back exactly to itself. And then I can connect these small Julia sets with paths inside the Julia set of the original f sub c. Okay, so conceptually, so I have f sub c, right, from, say, C to C, with C inside of the Mandelbrot set, and I could even denote it as the Mandelbrot set for this Hubbard tree. Somewhat inefficient notation, but it's not clear. Well, I could use external rays to make it more efficient, but and then I have this f sub c to the fourth from V0 to V4, which is the official, let me even write it as the Doherty Hubbard for renormalization. All right. So here we've defined this notion. We've observed that there are these small copies of the Mandelbrot set inside of the larger one, that for every parameter value in there, we can form this renormalization, and that this renormalization then has a type. It has that these small Julia sets for the renormalization are connected by the larger Julia set in exactly the same way as the attracting basins for the original dynamical system were connected in the Julia set. And that way we can define the type of the renormalization. And of course we could simply say where this C is coming from, like which small Mandelbrot set it's coming from. But this is a way of dynamically understanding the type of the renormalization. And this is not by any means a new idea, but I think it's important to kind of make this clear for what follows. Okay, and then okay, so okay, how should we say this? So let me just state the main conjecture. Okay, so there are various ways of saying this. So suppose kind of M, which is equal to M0 contains M, say, C1 containing, let's say, well, C0, MC2 is a nested intersection of small Mandelbrot sets, then this intersection, this infinite intersection, is a single point. Okay? So, I should say perhaps just a word about this nested intersection. Right? The idea is that it's possible for this renormalization to be further renormalizable. These pictures get kind of small, but you could imagine having some further renormalization here. Maybe this is the third power of the renormalization. So it's f to the fourth to the third. And you could keep nesting inside of this. And so you'd have a map. The point is that, okay, so, well, let me just say a few things. So first observation, so first, the theorem really Tsuryokos that if C is in M, then either C is in this intersection, this nested intersection of small Julia sets for some sequence, or M is locally connected at C. And in fact, we should continue. If this intersection is just equal to a single point, then M is locally connected at C. So what we can say, sort of by 1 and 2, is that the Mandelbrot set is locally connected if and only if these intersections is a single point for all sequences Ci with M sub Ci containing M sub Ci plus 1. Okay? So, part of the number one motivation for this main conjecture, certainly, is that it implies that the Mandelbrot set is locally connected, which in turn implies density of hyperbolicity, which in turn implies that you can draw an arbitrarily accurate picture of the Mandelbrot set on the computer. So, okay, so that's our first statement. And maybe I should make one more thing. So, sort of main conjecture. Let's say restatement of main conjecture. So it says, yeah. All right, so this will be nice. So suppose f sub c and f c prime are both infinitely renormalizable. Infinitely renormalizable, and I should again say a word about what that means, with a sequence of types, and let me say of relative types, and they're kind of given, you could think of them as given by Hubbard trees. So let me say H1, H2, dot, dot, dot. With the same sequence. In other words, then C is equal to C prime. Okay, so you can think of it as a kind of rigidity statement, right? In other words, if you have two maps in this infinite intersection, then they have the same sequence of relative types, which I define in just a second, and what we want to say is that they're the same. Yes?
Accept the symmetry.
Sorry?
Should accept the symmetry or?
No. Because if I replace this Hubbard tree with this reflection, its complex conjugate, I don't want to think of it as the same Hubbard tree. So, yeah, I mean, certainly because we could do lots of alternations. All right?
The order at the multiple points is part of the data of the tree.
Yeah, how the tree is embedded into the plane up to isotopy is certainly part of the data, yes. Okay, so infinitely renormalizable. So by relative types, it's kind of what I'm saying over here, right? That in this picture, if we blow up, if I erase something over here, and if I blow up this picture here, right, then I'm going to see, for example, 3 small Julia sets that are connected now inside of the Julia set of the first renormalization. And again, there'll be some ordering to those so that I get a Hubbard tree that describes how the second renormalization is derived from the first. And so we can take an absolutely arbitrary sequence of relative types. We can take an absolutely arbitrary sequence of Hubbard trees here and get an infinitely renormalizable map. We can get a sequence of small Mandelbrot sets for which these relative addresses are going to be given by this arbitrary sequence of types. And then the problem is to show that there's a unique map with such a sequence of types. Okay, so that ends part 1. We should move on to part 2.
Some special cases or for some relative types or?
Yeah, that's what I want to do in part 2. Okay, so all right, so 2 is sort of statement of results. Okay, so the first theorem of this kind, so I should say first, okay, so I should say, right, so, okay, so let me just talk a moment about bounded primitive type. So perhaps over here, there are kind of 2 possible Hubbard trees. So one simple example is, here's kind of degenerate looking Hubbard tree. All of these disks are just touching each other. And then here, well, I'll redraw a nicer Hubbard tree where there's some kind of space between the disks. And this is known as satellite renormalization. And it corresponds to disks kind of just touching the main cardioid. So for example, over here, and this is known as primitive renormalization, corresponding to small Mandelbrot sets that actually kind of have their own little cusp. And so the first theorem says that, so let HI be a sequence of primitive types with the size of HI, so I could say perhaps the period of HI less than some B. Okay, so this B holds for the whole sequence. Then the main conjecture holds. Okay? And so in the third part of the talk, I'll start to give some of the ideas, and hopefully the third part will come soon because otherwise we'll have no time. But let me state two other results. So the second theorem is, well, there's the sort of the molecule condition. There's a couple of ways of saying this. So let me just say the kind of getting somewhere in bounded time condition. So for this bounded primitive type, we have a sequence of types, a sequence of Hubbard trees, and they're all bounded in topology. So certainly something interesting should happen in a bounded amount of time. But we can generalize this to sort of this getting somewhere in bounded time condition. So it says, so this is a theorem with Mikhail Lyubich. And it says, again, suppose we have the sequence, so let HI be a sequence where there exists again this B such that for all I, okay, so for all of these HIs, there exists an arc alpha between two disks of HI such that, and this is maybe slightly informal, such that f to the b of alpha, let's say f to the b maps alpha twice over itself. Okay? So in some bounded amount of time, we have an arc between two disks of the Hubbard tree, and there might be many disks in between. And then in some bounded amount of time, well, it could sort of go up and go around, but it's basically mapping this arc twice over itself. So this would be alpha, and this would be f to the b of alpha. Okay, so in some bounded amount of time, it's mapping this arc twice over itself. And so that's clearly a generalization of this. And then, yes?
So it is for any two disks, the condition?
No, just that we just need that there exists an arc alpha in the Hubbard tree for which this holds. Yes. So then this main conjecture holds. All right? And that was I don't know, that was not too hard to prove, perhaps, given the machinery.
Twice, exactly twice?
It's just at least twice.
At least twice.
At least twice, yeah. So there's some stretching. There's something happening in a bounded amount of time, which I'm trying to have happen in this talk. And then 3 is the elephant eyes. So let me just put it in the most special case. So consider, so suppose the HI lie in the set so let me even just draw these. So here's 1. So what we can do is just go around this fixed point most of the time, and then at the very last step, jump behind the critical point, and then return. Okay? Then the main conjecture holds. Okay, so here, nothing happens in a bounded amount of time. Right? You take any arc, like this arc, so it goes to this arc, which goes to this arc, goes to this arc. You have to wait until it comes all the way around for anything to happen. So it represents progress, a step forward with the elephants.
It's called the molecule condition.
Yes?
Relate to terminology and say when the Mandelbrot set happens.
So, okay. Very well. So here's the Mandelbrot set. Here's the immediate bifurcations. Here's the bifurcations coming off of that, and so forth. This is called the central molecule. And it should be not hard to show that something happens. So the HIs satisfy condition 2 if and only if the associated centers, so we should have Mandelbrot sets, primitive ones, so flying out here, if and only if the CIs do not accumulate on the central molecule. Okay. So somehow the central molecule, that's sort of like, well, it's satellite renormalization, where in a way nothing happens. And then there's kind of no stretching of the Hubbard tree. And as long as you stay away from that, you get some stretching of the Hubbard tree in a kind of definite amount of time. Okay, that's just the combinatorial statement. Okay, so I have till...
So that proves MLC away from the central molecule, is that it?
No. It proves MLC, right? It shows this main conjecture. So you look at infinite intersections of small Mandelbrot sets, right? And you look at the relative addresses. So you look at how each small Mandelbrot set sits in the next smallest. And all of those have to be kind of uniformly away from the central molecule once you kind of renormalize them to the largest scale. So yeah, no, so it's nowhere near showing it outside of the central molecule. But it's progress. So, okay, so I have till 11:45? Okay, so, well, there won't be so much on the details.
You have to be away from the central molecule at every step.
I have to be, yes, away from the central molecule at every step of the renormalization.
The relative central molecule.
Well, if you like, yes, you could look at it either way. Right, you could have a sequence of relative central molecules and say I'm away from those. But I think what's better is you look at the sequence, you look at each small Mandelbrot set, you renormalize the next smallest to be the whole thing, and then you want to be away, uniformly away from the central molecule. Yeah. Okay, so I want to talk a bit about the modulus of renormalization, because this is kind of an essential idea, the modulus of renormalization. So, so the simplest picture is in this Doherty-Hubbard renormalization. Let me draw it something like this. We have this kind of u, v, f to the n here, and we can look at the modulus of this annulus, modulus of v minus u, like the modulus of this annulus here. And the problem is that the choice of v and u, so let me just write this here, choice of v and u is non-canonical. So there's what's known as the canonical renormalization, which allows us, among other things, to talk about the modulus of each renormalization. So the canonical renormalization, it kind of requires the Doherty-Hubbard renormalization even to be properly defined. But what you want to say is, suppose you have, okay, let's see if I can draw this in enough space. So suppose I have down here, I have some quadratic-like map, and then at the next stage, I have some renormalization. Okay, but what matters now really are these small Julia sets. So I have this outer domain V. And now what I want to do is say how much space could we possibly put around this little Julia set. So I form a cover. Here I could think of this as V minus the K, the small Julia sets, the union of the small Julia sets. Maybe I'll use a curly K for the union of these small Julia sets of the renormalization. And so then up here, I form a cover, V minus K RF tilde, right? It's the cover associated just to this element of the fundamental group, and then I can just plug that Julia set back in. And then the idea is that, let me redraw this picture slightly. I have this U. So this U is just, I have an inclusion here, and then I have the map, the renormalization of F. Well, actually, the original F, which is now quadratic-like. And what I want to do is to lift this up actually this picture, let's see, what I really want is, say, V3 and F cubed. Okay, so this is returning this guy to this guy. So I can take a lift here, this sort of V3, and actually I want to remove all this other preimage Julia sets. Okay, so I take the third preimage minus F to the minus 3, in this case, of K sub RF. And I take a cover of that associated again to the same place. And I get something that looks very similar. And now I have an inclusion and the lift. So I have a kind of lift of the inclusion, and I have a lift of the third power. So this will be an immersion. This one here will be an immersion. And this one here will be a degree 2 cover. So it's very similar to the Doherty-Hubbard renormalization. In the Doherty-Hubbard renormalization, I have one set embedded inside another. Here I have one set immersed inside of another. But by doing this, we allow a canonical definition of the renormalization that turns out to actually be much easier to work with. So we can get No, well, we still have a modulus, but we're not looking at the modulus between U and V. We have lost that. So we get a sequence so F equal R0, F, R1F, R2F, dot, 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 of canonical renormalizations and we let the modulus of this renormalization equal the modulus of sort of Vn. This is, you could think of that at the nth step, minus the small Julia set of the renormalization. Okay, I don't know if that's entirely clear, but what I mean is just that we have a natural annulus. We have a natural annulus right inside here. Right? And that's the modulus that we care about. That's giving us some space to work with. Okay, so sorry?
Does it depend on the choice of U and V in the beginning?
So no, because we can literally just start with the entire complex plane at the beginning. So that's a decent map here. It's still an immersion. We don't need a compact containment. And then at the first step, we get some disk, and so forth. So you could say you have infinite modulus at the beginning.
Did you start with polynomial?
Yeah, you start with a polynomial.
Polynomial, like Weinberg polynomial.
Yeah. Okay, so, and now we can introduce this idea, right, of if it's bad now, which might be stated about my talk, then it was perhaps much worse earlier. And there'll be a new slogan for those of you who've seen the old slogan in a minute. But so what this means, so the theorem, for example, so for one, in this bounded primitive type, we can say this, that for all, there exists, let's see here. Yeah, basically for all B, there exists this M0. Okay, so, well, we can just write it like this. So for all B, there exists this M0 such that, so if, if FC is infinitely renormalizable of B bounded primitive type, and R to the n, and the modulus of R to the n FC is less than this M0, then let's just say n is greater than 10, and the modulus of R to the n minus 10 FC. So if we go 10 renormalizations back, that was less than, say, M0 over 2, so it was worse. Okay. So that's an example. If it's bad now at time n, then it was worse earlier. And this shows that this modulus is never going to 0. That it has to, in fact, stay below, stay above M0. Right? It can never actually go below it. And then this implies main conjecture by somewhat standard method. So, but it was first written down by work of Lyubich, I believe. It was first written down by Misha. And then similarly, in the second case of bounded primitive type, so what we'd like to say in general, okay, so in general, so for general primitive type, we have this conjecture that, right, for all kind of ratios M, there exists some P, let's say P0 or something, and some M0, I believe, so that if FC is infinitely renormalizable, just of any primitive type, well, so really what matters here, let me just even say it's renormalizable. So just in one step, it's renormalizable of any primitive type with the HI kind of sufficiently large period, so at least P0, and the modulus of this renormalization being less than or equal to M0, then the modulus of FC is actually less than M0 over M. So it's actually much worse because M can be arbitrarily large.
Is that the period?
Yeah, that's the period. Sorry, I should just say period. Okay, and this is, so maybe I'll just say here.
So are you thinking that it's just never happens?
Sorry?
Are you just thinking that the hypothesis just never happened?
No. So here I stated it. Here I stated it as we start with, oh, I'm sorry. So I should state this more carefully. So if I have G, well, let's say I, F from U to V, this sort of what I call a pseudo-quadratic-like map that can arise out of this canonical renormalization. So a pseudo-quadratic-like map. Then, so let me just say RF here. So we start with any pseudo-quadratic-like map because I'm just taking one renormalization. And I'm saying you take any pseudo-quadratic-like map, you take one renormalization. And if this modulus is small, then the modulus after the next step will be even, the previous, if the modulus after you renormalize is small, then the modulus you had to begin with will be much smaller. And you can certainly start with a map, right? You can start with a quadratic-like map, let alone pseudo-quadratic-like map. You can start with a quadratic-like map with kind of arbitrarily small modulus to begin with, or arbitrarily small modulus around the small Julia sets. So certainly this hypothesis can be satisfied. But if you started with a polynomial and you had a sequence of renormalizations, the idea is if you had a sequence of primitive renormalizations, then it would never get that small, exactly for this reason. Okay, so, and then the idea is this conjecture, this has been proven in the cases that we talked about, proven for this molecule condition and these elephants. Okay? So I just have 10 minutes for the third part. So let me introduce the new slogan here. So it's really enough to show, the idea is it's really enough to show that if it's bad now, it was kind of not that great earlier. All right, so what does that mean? Well, we'd like to say, I mean, the real ideas here are contained just in showing that if this modulus is really small, then this modulus here, the modulus you had to begin with, couldn't be bounded below, or something like that. Okay, so let me just look at the elephants now. Let's just look at these elephants for a minute. Okay, because here we have unbounded type, and I have just 10 minutes. So, right, you could imagine that you just want to show that if you take the sequence of small Mandelbrot sets approaching the cusp, and you take the renormalization for each of them, that you want to get a lower bound on that. And that at least gives you some idea of the machinery that we're using. So, okay, so for these elephants, so the idea is that first, okay, when this modulus of RF is small, then this outer domain minus the Julia sets for the renormalization is degenerating. All right, so we could call that kind of pinched. And we can analyze. Okay, so what is this pinching? So here we have one of our elephant Hubbard trees. And this picture, it's really, we're looking at our small Julia set. Right, we're looking at our small Julia set, and we're trying to understand, like, the small Julia sets are arrayed exactly like this, and the whole sort of dynamics that we're dealing with is determined by this picture. And then we're trying to understand, like, why this modulus around, say, this zero guy is small. And so it has to happen, well, what's presumably happening is that there are these kinds of connections between this guy and the other guy. It's like this space, the extremal lengths of these paths connecting, say, 0 and 1 has become quite small. I did. Maybe I should use another color. Okay, so do it in green or something. But the whole point, so let's say, okay, I'll just use these boards. So kind of case one, well, okay, so when the kind of pinching aligns with the Hubbard tree. So here we're really specifically using this kind of elephant construction. We have all these guys, dot, 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 and then I have kind of -2 down here, and I could just write this as -1, and then going back to 0. And what does it mean to be aligned with the Hubbard tree? Well, the pinching is between these stis, or these small Julia sets, so it's really looking like this. So I have some sort of connections like this, and so forth, and then perhaps all the way over here. And I'm saying that these are the Julia sets that are getting kind of close together in terms of extremal length. And then the point is that the kind of, there's two things going on, right? I could put an annulus around each one of these. I could say, what's the largest immersed annulus that I can put around each of these? So I could call this A1, and I could call this A-1. Okay? And the idea is that this path family here connecting 0 and 1 then maps to the path family connecting 1 and 2 and so forth, going all the way around. Is that my time up? Sorry? 5 minutes. Okay. 5 minutes is plenty of time. So this path family, I mean, I'm introducing a million ideas because I have 5 minutes left. But this path family connecting 0 and 1, it maps by the dynamics to the path family connecting 1 and 2, and so forth. And the width of this annulus, so if I have, where's my yellow chalk? I spend 3 of my 5 minutes looking for the right chalk, which is probably not going to happen, so it gets recolored. So if this width here, if the path family kind of has extremal length, or let's say modulus, so modulus here, well, let me say width of the path family, which by which I mean 1 over extremal length of the path family. So if this width is, say, W, then what we expect is that this width is also W, and then kind of going all the way around, we expect this width to be about W. That it's just mapped all around by the dynamics. And because there's some stretching going from here all the way to here, we expect this to be kind of less than or equal to W. And so what we get is that the modulus of this A1 is about 2W. So it's roughly, sorry, it's 1 1 over 2w. Okay, so the greater w is, the shorter this extremal length, which means the smaller annulus that you can put in here. So the modulus around A1 is about 1 over 2w. And the modulus around A minus 1 is about 1 over w, or something greater than or equal to 1 over w. Minus 1 has only this one connection to 0, so there's hope for putting a kind of larger annulus in here. But then there's a paradox, because if I take this annulus here, I can pull it back all the way. This is very old. This is like in Kurt's book on complex dynamics and renormalization. I can take this immersed annulus all the way here and pull it back all the way back to here. I only can't pull it back. If I pull it back one more step, I have the modulus, but I can pull it back from minus 1 all the way to 1, which means that this modulus here should be greater than this modulus. Okay? And you see there's a contradiction. So that all goes back to this bad now, not that great earlier. Right? So it's saying if it's pinched in this very particular way, if there's kind of a small modulus around this central small Julia set, then you can push it all around. And what you get is a contradiction. And what we're really contradicting is that there's no pinching between these small Julia sets and the outer boundary. Okay, so what we're saying is there has to be some small extremal length between these small Julia sets and the outer boundary. And that's the statement of it being not that great earlier. So probably I should end here. There's a quite big question left, which is how do we get the pinching kind of neatly aligned with the Hubbard tree? And that actually is kind of the real work. And so maybe I'll just draw one last picture. One last picture for that. There's, in a way, a very simple idea of why that's true. Okay, so why is pinching aligned with the Hubbard tree? Okay, and well, maybe I'll just use the same picture with some new chalk. Purple, blue. We got blue is good. So the idea is just that maybe to draw a few more disks. If you had something that was going in some much more exotic way, okay, if you had something that was going in a much more exotic way, then what you'd want to say is that it was preserved by the dynamics. And so when you pushed it forward a step, it would kind of cross itself like this. And that would be a contradiction, because you'd have these two path families. Like if you look at a rectangle, right, if you look at the path going one way and the path going the other way, they can't both have short extremal length. So if we had some kind of short extremal length like this, it couldn't cross anything else of that form. And it turns out that it's easier just to study these kind of individual segments. So it's easier to study things, I'm running out of colors, but it's easier to study things that, if you imagine kind of cutting the whole thing along the Hubbard tree, and then just studying these segments connecting like edges of the Hubbard tree to edges of the Hubbard tree. And then those are kind of forced to, if they cross each other, they can't have small extremal length. That's the basic principle. And so everything's kind of forced to align with the Hubbard tree. Okay, so thank you very much. And if this talk was bad now, it was not that great earlier.